my dear colleagues, respected Pradyumna sir. Let me first introduce the speaker over here for today's webinar. He is a renowned person in the area of computer science engineering, Dr. Pradyumna Kumar Tripathy. He is working presently as a head of the department and associate professor in the Department of Computer Science Engineering in Silicon Institute of Technology, Bhubaneswar. He has completed his MTech and PhD degree in computer science from Utkal University in 2007 and 2015 respectively. He has more than 16 years of experience in teaching and 9 years of experience in research. His research interests include reliability analysis of interconnection networks, parallel distributed system, and topological optimization of interconnection networks. During his PhD, he has published more than 30 research articles in different reputed journals and conferences like IEEE, Elsevier, Springer, and other reputed journals also. So Dr. Tripathi is a life member of IITS, ISTE, WLA, and a senior member of IEEE. He has expertise in both research and development. He has guided more than 35 MTech students in their thesis work. He has received the award for his continuous contribution to excellence in teaching and research at Silicon Institute of Technology. He has also received many other awards like Rajlakshmi Memorial Best Engineering College Teacher Award from IST, New Delhi on 6th October 2021. Received University Foundation Day Research Award in 2020 from BPUT. Received Swami Vivekananda Pratibha Puraskar from her contribution in technical education for Evergreen Forum, Odisha Youth Conclave in the year 2015, and many other such awards are there. He has also registered 6 patents in his name. So rather I can say that it will be our privilege to listen something from him in his research area. So let me welcome Dr. Pradyumna Kumar Tripathi to start his webinar for today's talk. Sir, please. Sir, you are muted.
Oh, sorry.
Yeah.
Thank you, madam, for such a warm welcome. Actually, I think I am audible now.
Yes, sir, you are.
So, should I share my slide?
Yes, sir. Yes, sir.
Okay. Let me share my slide. Okay. Welcome everyone. Actually, today's topic that I am going to deliver over here is the cost and reliability issues in interconnection networks. So this was my research area as well as my the PhD area. The PhD area I have done the work on the same area. That is the reason for which I have chosen this topic. Hope some of you will get benefited, may be interested to work on the particular field. Although there are various versions of these interconnection networks are there, and people are working in different correlated area with the interconnection network. Anyway, I will just put some light on this, and I will talk on different issues on this which are associated with this interconnection network design principles, and what are the resource scopes are there. So topic of today's discussion is cost and reliability issues in interconnection networks. So my presentation is here limited. I'll go for some introduction. I will introduce what the interconnection network is, what are the factors that affect the design of interconnection network, then we'll go for the cost and reliability issues, and we'll go for some literature survey, what are the issues associated with design, some algorithms which are being designed or the papers published for addressing these issues. Then we have conclusions and some references. Okay, so I'll start it from the very beginning. All of you might be knowing about the Moore's law, right? what the Moore's law says, that the number of transistors on a microchip will double in every 2 years. It's actually it's actually an empirical thought that has been given by Moore, that the number of transistors on microchip will doubles every year, and which was found to be true for some years. But after that, it has seen that it's not only double, it is more than that even. If you look into this graph, this is the image that is being taken from the Google. The data source is from Wikipedia. You can see over here, for example, 1974 is this number of 5,000 number of chips. Maybe in 76 or 78, it's almost 10,000. And 82, if this number of chips, maybe in 84, it's a double of more than double even. So this trend continues maybe up to 2004, 2006. The number of transistors, doubled up to 2000, around 2004, 6, around that. But after that, the designers, they thought that why to go for increasing the number of transistors on the microchip, because there is a limitation on the space, because the microchip has a limited space and all these transistors has to be put on these microchips. That not only leads to a constant on the space, that also leads to a constant, the more heat generated, and you need to cool it, all the time. Therefore, they go for multi-core systems. Instead of one processor, now they will have two different processors with smaller processing speed. Instead of increasing from 3.4 to 4.3 gigahertz, rather they go for two number of cores, each may be of 2.1 or 2.2. So that is why the core concept came. Then it comes with the dual core or core to duo processors. Then you say quad core processors, octa core processors. Even the mobile phones that you are using may have hexa core processors as well. Because the heat generation, space complexity, and the cooling are the main factors for which the processors are now comes as a number of cores. So if you go for a single supercomputer system, you will have one CPU, and you may have a number of memory modules which is shared by the CPU. Not only memory modules, maybe have some disk. Now this is being shared by a multiple number of users. This memory is shared by this processor. You may have the entire memory is now we say as a shared memory. So it is somehow we can say it's a tightly coupled system. In one, the entire memory is being shared by a processor. So it's a single supercomputer architecture. Next is comes to be a multiple PC on one location. You have one PC on which you will have multiple number of processors and multiple number of memory modules, as well as the disk. And these are being shared by a number of users as well. So these kind of systems we say parallel systems. The number of tasks can be run in parallel. You can see over here the processors, memory, and the IO devices. So separate CPU and separate memory. But these are on one machine, on one computer actually, on one computer. So a computer has multiple processors and maybe have multiple memory, but these memories are shared memories. The next generation comes with the processors and memory, the similar to the previous one. The only thing is that now these can be accessed anywhere, accessed anytime, anywhere with the mobile devices. These users are now called each of the user now is called the virtual admins, right? So multiple PC in different locations. Now these are in different locations and we want to access them, right? That leads to distributed computing. That leads to distributed computing. So how you differentiate is a parallel systems with parallel computing with a distributed computing. Why I am calling this, why I am discussing this parallel and distributed, because the concept of interconnection network will be derived from here only. Just look into the system that these computers, what you see, are all autonomous computers. What do you mean by autonomous computers? are the computers which can start and stop of their own. They don't they don't depend on other computers to be started or to work upon. Now each computer has their own memory. So these are loosely coupled systems. They have their own memory. These are basically loosely coupled systems. If you look at the parallel computing, one computer has multiple processors and they have common memory. So those are tightly coupled systems. Because all the processors are on one computer, it is being governed by a single clock. But here these are autonomous computers, everyone is having one clock. So the transfer rate among these devices is quite low as compared to the parallel systems. Now thing is that where to use parallel and where to use distributed systems. Parallel systems are basically being used where you need a high computing. You give a task and you want scientific computing, you give a task, you want it with a very high speed. Distributed computing is basically being used when you have more reliability or availability, particularly like your ATM machines. The ATM machines, you log into anywhere, it is being validated and you can access over there. So this is the basic difference between this distributed computing and this is the parallel computing. In parallel computing, we will have multiple number of processors, and all the processors share a common memory, right? All the processors have access to this common memory. Whereas if you look into the distributed computing, these all are individually are autonomous computers. Every processor has its own memory and they do interact with each other through message passing. Through message passing, they will interact with each other. So these are basically loosely coupled systems. Correct? Any point of time, if you have any doubt, you can interrupt me. So this is basically the difference between parallel and distributed systems. If you talk about the memory, the parallel systems are tightly coupled and distributed systems are loosely coupled systems, and therefore it uses the message passing. They are having the shared memory. And it has a global clock for parallel systems, and for distributed systems there is no global clock. So controlled synchronization algorithms are required. So you need some controlled synchronization algorithms because you don't have any global clock. The processor interaction, if you look at the parallel systems, I said it is a very high speed. It is in term of TBPS, terabytes per second, whereas in distributed it may be in GBPS, gigabyte per second. The main way to use the parallel systems when you look into the performance or scientific computing. Distributed system where you'll see when you look into the reliability or availability or resource sharing, and then you will go for distributed systems. Now question is that how these computers will be connected. This is one computer, this is one computer, how these will be connected. Or if you have some processors and memory modules, although it looks like one memory, but this memory is consist of a number of memory modules. What is the pattern in which they will be connected? It is not that we will connect them randomly. They will be connected in a particular fashion so that less power consumption will be there, less cost will be there, it will be more reliable, it will be more effective. So what is how these computers or the processors or memory modules need to be connected? That defines the interconnection network or topology. This interconnection topology is of two types, either a static or a dynamic or indirect. It's a static network or indirect network or dynamic network also. In static network, these are suppose, for example, these are the processors and these are the processors and these are some switching elements. It uses the switching elements to switch, right, to send the data. Now, if these links between those processor and the switches are fixed in nature, if you cannot alter, then we say it's a static network. For example, bus, ring, star. You might be knowing all these topologies before. So these networks has a predefined topology, and this you do not change. You don't reconfigure it. Once it is designed, it is being fixed. But if you look into indirect network, if the links can be reconfigured, let the link is over here, I can remove and add it to some other locations. If the links can be reconfigured, then we say it is an indirect network. Correct? So let us define this interconnection network: a complex collection of switches and links which facilitates the effective data transmission among the processing elements. So it is actually to the processing elements or memory modules. Now these are connected for what? For efficient data transmission among the processing element or between the processing element and memory modules. So we have two different types of networks, interconnection network. One is static interconnection network, another is dynamic. As I said, static consists of point-to-point fixed communication among processing elements. So you cannot reconfigure it. For dynamic interconnection network, connected to one another dynamically by switches to establish path among processing elements and memory modules. So we'll have what? We'll have links between the processing elements and the memory modules. Correct? So memory modules, maybe no, so links between these can be dynamically reconfigured. But what is the need of this interconnection network? These are some being listed over here. That plays this interconnection network plays a central role in determining the overall performance of a multi-computer system. I have written over here multi-computer system. However, this also works on the multi-processor systems, because the pattern in which these links and these switches are being connected, that determines what is the outcome, what is the performance that it can yield. It should be designed to transfer maximum amount of information within the least amount of time. So it is not only the time, cost and power constraints, so as to not to bottleneck the system. We have given with a time constraint, we may be given with a cost constraint or power constraint. Within that, what is the maximum amount of information it can transfer? So given a set of switches and links, we have given with a cost. Now problem is being defined as how to design the network so that the network will be efficient or reliable within this cost constraint. As you have a network, the fault may also occur. So your network should have ability to function in presence of some faults in the network. In spite of some failure in the network, it should revive itself and could function, give the performance as it is being designed. There are some properties associated with interconnection network. Those are degree, diameter, cost, and reliability. These are not only four properties. There are many other properties are there, but these are the most important properties that are associated with the interconnection network. The degree says the number of nodes adjacent to that node. How many nodes are connected to a particular node? That is the degree of the network. More the degree, that means connectivity is more. More the degree, the connectivity is more. The diameter is defined as the longest part within any two nodes on the network. Diameter actually says we'll find the shortest distance between any two nodes on the network. Then among those we'll find out the longest one. That gives the diameter. Lower the diameter signifies we have less number of hops to transmit the data. The cost here defined as the degree into diameter. The objective is to reduce this cost. The reliability is a term which is very important over here. The reliability says the probability of a system to do its required function for a given period of time under some prescribed conditions. It is nothing but is the probability of success, or success probability, I can say. As the probability value varies between 0 and 1, so reliability value is also varies between 0 and 1. So we require what is the success probability of the network to perform what it is being desired, what it is desired or expected from the network for a given period of time under some constraints. Now, if you go deeply into reliability term, there are three different types of reliability that is being associated with a network. Now, when I am saying interconnection network, it is not only for the parallel or distributed systems. These interconnection networks can be applicable in practical scenario. For example, traffic management system. Each of the traffic posts can be considered as one node, and connection between them may be the links. You may have the cities are maybe considered as one node. The roads between the cities can be considered as links. The telecommunication network can also be considered as an interconnection network. So if we are optimizing a network of any of this kind, that means you are also optimizing a particular solution. There are many problems, practical research problems which that may arise. For example, in a particular city or in a particular area is affected by cyclone and that area is being damaged, and you need to transfer, communicate to that particular area. There are some paths which are being blocked. You have to find out what is the shortest route through which the data or the communication can be sent. So this problem can be mapped into various real life problems as well. So that leads to various research areas. Anyway, the reliability, there are three different types of reliability that are being associated with a interconnection network. The first kind of reliability, which it's almost every network that requires, is the network reliability. The network reliability says the probability that all the nodes of the network are connected. They given some of the nodes and links. There might be a chance that some of the links may get failed. In spite of the fail, the network should operate. The nodes should be connected. If some of the links are failed and still we could able to connect to the particular all the nodes, then we say network reliability exists. If any one of the node could not be reached, then we say there is a failure of network reliability. So network reliability is all to all. All nodes should be connected to every other node in the network. There is another term is your terminal reliability. The terminal reliability says the probability that at least one fault-free path exists from the source to sink. For example, there is given a network. I have designated two different designated nodes are there. Are laid down which are for communication. We want to communicate from one city to another city. We are not bothered about the other cities. There may be failure of number of roads, but whether the data can be reached from the source to destination or not. For a given source to a given destination. If you have at least one path, fault-free path exists, then we say terminal reliability exists. If it is not, if no path is found, then we say terminal reliability fails. So it is a point-to-point or one-to-one communication. One-to-one communication. Similarly, we have a broadcast reliability. The broadcast reliability says the probability that a given information should be broadcasted from a given source node to all other nodes. That means from a node, it should reach on all other nodes. It's a one-to-all reliability. So for a network, we may require any of these, maybe data reliability, terminal reliability, or broadcast reliability. The next, coming to the topological design. The topology means what? The arrangement of these links and the pattern of connecting these nodes and links. The pattern of connecting these nodes and links is the topological design. It involves the determination of the subset of links that should be established for an effective communication among the network nodes. It is mostly determined by geographical and physical constants. So given a set of nodes and a link, we need to design a topology. We want to design a topology. Correct? So it refers to the rearrangement of links so as to maximize the objective function. Maximize the objective function means we may want to maximize the reliability, or maybe we want to minimize the cost within a given set of constraints. Given set of constraints, maybe with the budget constraint, maybe a cost constraint, or maybe power constraint. So you have given it a set of constraints. So you have two things. So it actually maps into a optimization problem. It maps into a optimization problem. We have to maximize or minimize a thing given a set of constraints. The way you solve any optimization problem, similarly you will formulate it as a maximization problem or as a minimization problem, and then the way you solve a maximization problem, like a convex optimization problem you solve, similarly you can solve, and you can get the solution for the same. So the factors affecting the topological design of interconnection network are reliability, cost, power, and flow. These are the things that affects the design of IC. That means when you go for designing of interconnection network, you want the high reliable. My network should be high reliable. So reliability of the system should be high in order to guarantee communication. I want the cost should be low. The cost of the network should be less in order to decrease the communication overhead. More cost should not be involved. It should have less power consumption and maximum flow. The topology must consume less power for this operation, and maximum amount of data should be transmitted among the nodes through the links. So it is not very easy to design a interconnection network, because we need to maximize certain things or minimize certain things under some constraints. So the cost of network depends on what? The cost of the network depends on topological layout, cost of the link, reliability. The topological layout of links means what is the order in which the links are being established, cost of the links, and reliability of the links. The reliability of a network depends on what? Reliability of nodes, reliability of links, and the topology. So you can see over here, the most cost, whether it is a cost or reliability, they are depending on this topological layout or network topology. So it is highly essential to design the network or topology in such a way that it should be more reliable and takes less cost. Looking into the review literature, there are various algorithms that are being proposed for reliability estimation and optimization. Some are based on the reliability estimation. Reliability estimation says how to compute the reliability, because this reliability computation of a network is a NP-hard problem itself. It is, it cannot be solved in a polynomial time. So there are various approaches that are being proposed. Some are based on spanning trees, some are binary decision diagrams, some are based on chord set and pass set methods, simulated unlinked, state enumeration, Boolean algebra, SDP, factoring theorem. These are the different approaches that are being used for reliability estimation. Similarly, there are various methods as well. There are various methods that are also being used for topological optimization, solving the topological optimization problem. Those methods can be broadly classified into two categories. One is, some are based on the enumerative approach and some are based on the heuristic approaches. The enumerative approaches are like branch and bound, spanning trees, shrink and search, and dynamic programming. And heuristic approaches based on ANN, genetic algorithm, and colony optimization, simulated unlink. So these are heuristic approaches. These enumerative approaches although gives correct answers, but it may not be suitable for when you go for the large scale networks or network with large sizes, because there is a large computation over it. But these heuristic approaches, they give the near optimal solutions. Actually, they give near optimal solutions, but however, again the same problem, we may not get the exact solution for the same. So there are some issues as well as the enumerative approach. What are the issues in enumerative approaches? Are exponential time complexity, poor and complex reliability expressions. Exponential time complexity, because if the network size grow in network size, results in grow in computation time, and in some time it becomes infeasible. This duplicity in finding the chord set, path set, and spanning tree. If you are going for chord set, path set, or spanning tree based approach, it may result in more, duplicate number of chord set, duplicate of number of path set. Then you need to remove them. Sometimes it suffers from combinatorial tree explosion, and it's only confined to some limited networks of smaller sizes, and difficulty in determining the parameters in the generation of two large combinatorial trees for large size networks. There are some heuristic approaches as well. The specificity of the ANN model to certain networks, because this ANN may not be practically applicable to all the networks. So inputting information to the ANN is very fast. Validation of the data set are on one of the major issue. If you go for genetic algorithm, the performance of GA depends on selection of the initial population. If your initial population is a good population, that may your convergence may be faster. If your initial population is not selected wisely, then it may convergence rate will take some time. It is a computational overhead, and only for getting near optimal. So we are only getting the near optimal solution. We may not reach on the exact solutions. So that is the motivation for designing what? Design of new methods for exact and efficient evaluation of different reliability measures of interconnection networks. So one is evaluation of the exact evaluation of the reliability of the network. Second one is design of new algorithms for topological optimization of interconnection networks for large scale parallel systems for maximizing the reliability or the minimizing the cost with some given constants. So now our problem is now of two folds. One, we should estimate the reliability correctly. We must estimate the reliability correctly and efficiently. Efficiently means within a given amount of time. Second one is we'll have a topological optimization problem where design an interconnection network within some constants. For solving these approaches, there are various algorithms are designed. Some of the algorithms that is there in our paper, in some papers I have also some research papers I have worked. For some of the papers I am being presenting over here. One says it will generate the minimal chord sets. I'll say you that what are the chord sets. So it will generate the minimal chord sets and disjoint that implicitly. Therefore, I am saying the self-generating disjoint implicitly to generate the reliability expression from which the reliability can be computed. Now, before going to dash, I must say what is chord set. The minimal chord set is the number of links that may be removed from the network. The number of links that may be removed from the network so that it will make the network disconnected. It will make the network disconnected. For example, if I have this is network. If I remove these two links, the network will become disconnected. If I remove D, E, F, the network will be disconnected. If I remove B, C, E, G, this will make the network disconnected. So I'll say each one of these is one chord. Correct? So these are the chord sets. If no subset of a chord set is another chord set, then we say the minimal chord sets. For example, HI, if HI is a chord set, then no AHI cannot be minimal chord set because already HI is a chord set. So our objective is to generate all minimal chord sets. From the minimal chord sets, we will frame the reliability expression, and from the reliability expression, we will compute the reliability. Correct? So that is the objective of this research work. So these are the algorithms. I am not exactly going through the algorithm. I am directly explaining that how the terminal reliability of a given network can be computed. Correct? So you are being given with a network. This network is having 6 nodes. This network is having 6 nodes and some links. 9 links. So this network is having 6 nodes and 9 links. This is a This is a benchmark network called ARPA network actually. So this network is having 6 nodes and 9 links. Our objective is what is the probability that the node S is connected to the node T. So I have designated 2 nodes S and T, source and sink. What is the probability that the source and sink nodes are connected? Correct. So we are using a chord set based, a minimal chord set based approach. So look into this process of creation, that how this chord set will automatically be generated. Very interestingly, it has been done, and its algorithm also efficient algorithm. I will discuss that complexity of the algorithm. So what we have done over there, we have taken all the nodes. We have taken all the nodes except the source node. So look over here, X is the set of nodes except the source node. So what we have left with? We have left with 1, 2, 3, 4 and T. So T 1, 2, 3, 4. So how many nodes are over here in this set? There are 5 nodes. There are 5 nodes in this set. So we'll start with the first working set. We'll start with this one T. We'll start with this T. Correct? So first I'll take a set W0 equals to T. So T is the set one set with T. What are the links associated with T? Is the H and I. What are the nodes associated with T? This is H and I. That we will consider. For the timing, remember, we will start with the first node 1 is the T. Next we will see, we will generate W1. What we have computed now? W0 is T. The next one will compute W1. How the W1 will be computed? What are the nodes which are connected to this T? 3 and 4 are connected. So T3 and T4. But this is not the sufficient condition. It says that suppose T3 I take, by removing this 2 T3, whether rest of the nodes are connected to the source? Yes, these all are connected to the source. So I'll take T3. Let I take T4. If I remove T4, the rest of the nodes are connected to the source or not? Disconnected. So I take T4. I believe it is understood. So what I have taken with the T is terminal. I have taken T3 and T4, and I have checked by removing T3, all other nodes in the network are also connected. Similarly, by taking T4, if I remove, then all of the nodes are also connected. So T3, T4 are valid sets. Now I'll extend it to W2. In W2, what we'll do, along with this T3, I will add the node which are adjacent to 3. For example, T31. If I take T31 and I remove it, rest of the nodes are connected to source. So T31 is a valid set. T32. If I take T32 and I remove it, T32, whether all the other nodes are connected? No, because 4 is disconnected over here. If I correct T3 and 2, so 4 is not over here. So therefore, 2, 3 and T is not a valid chord set. Then we suppose T4 and 2. T2, 4, I can see over even if we can remove, rest of the nodes are connected. And similarly for T3, 4. So we have generated all the nodes for the W2 set. Exactly in the same manner, we will generate for W3 and W4. So we have generated the node sets. So we have generated the node sets for each of these categories. T3 are DEGH. This is HI and DEGH. What is the common over here? The common over here is the H. The common link will be discarded. So we are left with DIEG, IDEG. H is actually discarded. So we'll take the H bar. We'll take it as H bar. DEGH H bar. I hope it is understood. Any point of time, if you have doubt, you may interrupt me. Exactly in the same way, if you have T4, so then we have it for T it is HI, and for 4 it is FGI. For 4 it is F, G and I. Correct? So the common is over here. What is the common? I is the common. Correct? So I is being discarded and we have left with F, G and H. So what is the final set over here? We have HI. Previously we have got. Here we got D, E, G and H bar. D, E, G and H bar. Here we get H, F, G, H, and I think that nodes will never fail, but for our assumption, we have taken the nodes and are perfectly reliable. And the failure of links are S independent. That means the failure of link doesn't give rise to the graph. So we have written R of G. So objective is to maximize the reliability subject to this cost constraint. That means the summation of the cost should be less than the maximum cost that has been defined. That is a now objective function. So now how to solve this problem. So we have having some we have a genetic algorithm approach for the same. These are spanning tree definitions that you already know. Spanning tree is the maximal set of edges of graph that contains no cycles and minimal set of edges. So 2, 3, 4 are 1. All other nodes are 0. For example, node 3 is connected to 1 and 4. So 1 and 4 it is being connected. All other nodes are 0. Correct? So this is the way it's a binary encoding. The network is being now encoded. Had it been a fully connected network, then it would have all the nodes. These all are 1, except the diagonal elements are 0. There are two different encoding. One encoding that you have discussed over here is the network chromosome encoding. We have a gene level encoding as well. The gene level encoding is gene we see over here is a path from source to destination. A path from source to destination, we define it as a gene. Suppose there is a path S1, 2, 3, 4 T is a path, or S1, 3, 2, 4 T is a path. So these are two different paths. So these are also being encoded. Suppose, for example, 1, 2, 3, 4 T. So I bring this 1, 2, 3, 4. So these I borrow it from there and put it over here. Similarly, I will bring this 1, 3, 2, 4, 3. Those rows I will bring and put it over here. So this becomes the second path. This is the path 1 and this is the path 2. This is gene encoding. The previous one was chromosome encoding or network encoding. Gene encoding refers to the path encoding. So we'll take the initial population. Initial population initially will take two minimal spanning trees. As you know that a graph may have a number of minimal spanning trees. So we have two minimal spanning trees over here. We'll take one on the cost by reliability ratio. So we'll take cost by reliability because we have taken what is it is a minimize the if you recall it is a maximization function of RG. So we have taken maximize 1 minus R. That means to see. So we have two spanning trees over here to T1 and T2. One is the cost to reliability ratios and 1 minus R. Now look over here. This is generate all paths from 1 to we have n number of paths are generated, right? So what will do we do? Merge each path with T1 and T2. Correct? So this is the spanning tree which connects all the nodes. This is a path from S to T. So this is a spanning tree and this is a path. So we'll merge the path with the spanning tree. We'll merge the path with the spanning tree so that the resultant network is this one. So you can see that this was not there, it is being added. The edges which was not there, but there is present in the path is added. So this is the resultant one. So this is the resultant of adding a path to the spanning tree. So we perform a single point crossover at any common node so that it ensures the result child are also S to T path. I will show you that the crossover of two childs, child 1 and child 2, So what are these child? These are S to T paths. Also results in another two paths. That I will give an example. Then what do we have now? We have spanning tree 1, spanning tree 2. We have child 1 and child 2. And whenever you merge, out of this we choose the best 2 with the reliability value. Correct? So now you look over here. As I said, the crossover will occur. See that how the crossover ensures the result in generating new paths only, S to T paths. So this is the spanning tree 1, S to T, S1, 2, 4, T. This is the spanning tree 2, is S2, 3, T. So what is the common over here? Which point is the common? 2 is the common. So we will have crossover on this common point. If you have crossover, this 3, 2 will move over here, this 4, 2 will move over here. You can see S1, 2, 3, T and S2. So these two are nothing but these are two paths as well. So gene level crossover also ensures that two paths are being generated. Correct? And you have to remember that if there is a cycle, for example, in between S to T, you can see the two, there 2 times 2 will appear, 2 is appearing. So we can remove this. This is actually a cycle. We may remove it. But that results in S170. So if any cycle is there, we must remove it. We must remove it. Correct? And that was the gene level crossover. Gene level means the path crossover. The second one is the chromosome level crossover. The chromosomal level crossover is nothing but two networks. We are actually crossover of two networks. Network 1 and network 2. For example, this is the network 1 and network 2. We have crossover point is 4. Suppose 1, 2, 3, 4. This, in this point we have a crossover. So these two are replaced with these two. So these two, the last two columns are replaced, are exchanged with these two columns of network 2. Correct? But unlike gene level crossover, the crossover of two chromosomes may not always produce two valid networks. Crossover of two paths always produce two valid paths, but crossover of two chromosomes may not always produce two networks, valid networks. And that is the reason for which we check for the validity of, we check for the validity. We check for the validity that if there is a no, if there is a 1 from ith bit I to j, that means there should be a 1 from j to I. If there is 1 from I to j, there must be 1 bit from j to I. If it is not there, you set it. So that we have just mentioned over here. If there is I to j bit, there is a 1, we must set it to 1 over here. J to I must be 1. If I to j is 0, then j to I must be 0. So that we have discussed over here. That we have presented over here. Check for validity operator. Correct? Then we have the mutation operator. The mutation, sorry. Then we have a mutation operator. The mutation operator says that we try to maintain two connectivity for every nodes. Every node must be at least two connected, right? So to maintain that, we use a mutation operator over here. So we first figure out that how many nodes is having the degree less than 2, either 0 degree or 1 degree. If it is 1, if there is only one node, then we'll join with the least cost. If there is exactly 2, we directly connect them. If it is more than 2, if there are more than 2 nodes which is having degree less than 2, then what we do, then we find out in this way. For example, I am taking and given an example. Suppose these are the 5 nodes, 1, 2, 3, 4, 5, and these are the links. Correct? So node 1 and node 5 is having degree 1. there are degree 2 is only 2 is having degree 2 and node 3 is having degree 3. Correct? Node 3 and node 4 is having degree 3. So this is N1, N2, N3. Correct? And these are the links 1, 2, 1, 3, 1, 4. So all the links and the cost is suppose given. Correct? For example, C35. C35 is this one. Let it is 3.5. Let it is. Now we have C1 to 2 is 2.7. 2 to C25 is 3.2. Okay. So if I have from 1 to 5, 1 to first to 5 is 5.9. But if that is a direct link from 1 to 5, it is 3.5. The direct link from 1 to 5 is 3.5. But if I am moving from 1 to 2 and 2 to 5, it costs to be 5.9. So it is better to connect this 1 and 5 directly. I hope it is understood. So C1 2 is 2.7, 1 to 2 is 2 to 7, 2.7, 2 to 5 is 3.2. So instead of adding in this way, I can directly join the link 1 and 2 5, which cost 3.5. So we compare these two values. This is the minimum cost, and we join it. 1 and 5 are being joined. So every step we are optimizing. Well, every step we are optimizing the cost over here. Now this is the final algorithm. This is the final algorithm. We generate the initial population. We select any two paths, any two S to T paths. We go for gene level crossover. We pop two networks P1, P2 from the population pool. We apply the chromosome level crossover. We check whether it's a validity or not, then apply the mutation. Then we compute the reliability for chromosomes and find the maximum one over here. This is the total entire algorithm. And this algorithm we have applied on various kinds of network that you can see over here. Network with even larger nodes and links. Now with some cost constraints we have computed with some mutation rates, and we have seen that it has generated. This is the computed reliability value, computed cost and reliability value. So you can see over here every time it is computed within the maximum cost. The maximum cost that we have taken 355, it has optimized within 350. We have taken 380, it has optimized within 365. This is 625 and it has optimized with 605 and with reliability, good reliability values as well. The optimal networks are being generated. Correct? So what we have presented over there is genetic algorithm based approach for addressing the topological optimization problem to optimize the terminal reliability with some predefined constraints. We have used the two level crossover as well as the chromosome level crossover now for better convergence. The chromosome encoding crossover operator check for validity and special mutation operator that always ensures producing a feasible two connected network topology. Net two connected means at least two of the nodes, every node must be two connected. This is the two algorithms that I wanted to share with you. There are various scopes that is available for this interconnection network. The on-chip networks actually uses on the background, it uses the interconnection network. Nowadays the cloud computing that you go for, cloud computing or edge computings, in cloud computing servers are connected through the network. The background is a parallel systems. If you go for edge computing, edge cloud computing, even they are connected to the interconnection network. So if you want to build your research, if you have interest on this research area, then you can apply these things on various fields. It is not only for parallel systems, you can go for apply the concepts on various other systems like wireless sensor network. We can apply it on chip networks. We can apply cloud network, edge computing networks. So on various networks it can. We have I had another algorithm to discuss, but I think it's already time. This algorithm was nothing but The same way, the way we have computed the two-terminal reliability, the network reliability also being evaluated. This paper was accepted in IIT Bombay, a conference in IIT Bombay. The similar way we have computed by taking the chord set and considering all the nodes, connectivity of all the nodes. And that is the uh, which the reliability is being computed. In every case, we have taken the cost and reliability as maximizing the reliability and cost as the constraints. So these are the conclusions for today's discussion. We see we have two terminal reliability evaluation of interconnection networks. A proposed algorithm we have seen. We have compared this algorithm with some similar approaches, and we see how it is efficiency. We have discussed the topological optimization and how to produce the reliable topology. We have discussed with how to compute the exact network reliability estimation and how it is being applied on some sample benchmark networks. So there are various, these are some publications from the work that I have discussed now, currently discussed today, the work that I have discussed, from which these are some of the publications and some references as well. So any queries?
Sir, I think there's a question in the chat box.
Okay, let me answer this. Okay. 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 How much time the algorithm takes to compute? Will it be useful for network with thousands? Oh, very good. So question is how much time the algorithm takes to compute? The first thing is that is a very good question. The first, for computing the reliability of the network, it's actually a NP hard problem. However, the first algorithm that I have presented, it takes a linear time. It's a linear time algorithm. If you look into the algorithm structure, you could able to find out what is the complexity of the algorithm. So if you look into this algorithm structure, it is linear in nature. The time complexity of algorithm is found to be linear in nature because we compute, we traverse it actually over all the links. So as we are traversing to all the links once, so we claim it to be a linear algorithm. But for second one, topological optimization, it is a heuristic algorithm, so we have not computed the time complexity. The second question from the same, would it be useful in a network with thousands of nodes? Well, of course, this will be used, but thing is that if when the number of nodes is very large, it becomes intraceable, and therefore, when the number of nodes becomes very large, we have to go for some heuristic approaches. Instead of going for some deterministic approaches, we should have to go for some heuristic approaches, maybe some genetic neural simulated unlink kind of thing. Will it be working effectively in WSN? Yes. We are for current work is on. I am trying to put it in, applying it on WSN so that your nodes. No, we have to think of that how this WSN works and how the my work, my ICN can be imposed on this WSN because those are the sensors nodes, and what is the range of the sensor nodes, how the connectivity, looking into the properties of WSN, this ICN can also be applied. There are some papers also for computing the reliability of WSN. There are some works which carried out on IIT Kharagpur by Rajesh Mishra. You can refer those papers as well. Any other queries?
Thank you, sir. Indeed, it is a very nice talk, I must say. One simple question is there. The different parameters for interconnected network, as you said, are the nodes, number of nodes, then the reliability and cost, I think. So,
Yeah.
can it be thought of in the way of transmission bandwidth, maybe a parameter?
Yes, yes. Actually, these are the some parameters that I have discussed. If you go for communication network, you have bandwidth,
Yeah.
you have there are various parameters, lead time, you have communication overhead. There are many other parameters that can be imposed, and there are a lot of application on the communication network as well. This
Actually,
intercommunication.
if you'll think of incorporating this interconnection network in designing a data center, then I think bandwidth
Yes,
be a vital
play even
parameter for.
yes. Yes, yes, that can be. That can be. Your bandwidth plays a vital role over here there, and your communication cost, even communication
Yeah.
cost also plays. Yes, that is also can be considered.
Then again, the length of the links will also be can be treated as a significant parameter.
Yes, actually,
Other many things. Yeah.
actually looking into the practical scenario, to what are the parameters to which you are giving the importance. Looking into that, we
Yes.
are actually
Yes,
designing the
yes,
system.
sir. Yes,
Network.
sir. Oh, thank you, sir.
Thank you, madam. May I leave now?
Sir, I have a question. Sir,
Uh,
sir, the flow control methods, can they actually have an impact on how the network is optimized?
See, actually, we are not exactly going through the network or passing of data. Actually, we are going for designing of the network. Actually, on the it is not about what how the packets are being transported or flow control mechanisms. We are discussing about how the network can be layout, the layout of the network, of the physical layer, we can say. So in
Okay,
that
okay.
case, so it's on the design part. Before designing, what we should do, that is actually interconnection.
Thank you, sir.
Okay. Thank you, madam.
Sir, Uh, on behalf of the Department of Computer Science, SOA University, I would like to thank Pradyumna sir for giving us such a broad and such an insightful discussion on parallel and distributed networking interconnection network. Sir, our students have definitely benefited and they would like to get in touch with you. So if you are allowing, sir, we can share your coordinates. I think our PhD students are also attending. So if they also would seek the PPT, and if you are sharing a write-up, so we really look forward to that. Sir, I really
Sure.
thank you. Sir, I really thank you for your time and such a bright discussion on this topic. I also like to thank the participants for patiently listening through it. Tapaswini ma'am for arranging such a wonderful speaker and such a challenging topic which was so nicely explained. I would like to thank the organizing team and our HOD, Dr. Tripathy Mishra ma'am, for conceiving the whole idea. So this is our 49th lecture actually of the SOA weekly academic lecture series from Department of Computer Science. And with the support of all the faculty members, we have come this far and we really look forward for other possible collaboration with you, sir. Thank you, sir.
This is
Thank
actually great. I'm feeling great by attending this conference, this talk, and
sir.
such kind of things should be encouraged because the students are the PhD students are also being exposed to the various domains. The what are the
Sir.
research institute initiative. Thank you all.
Thank, thank you,
Thank
sir. Good evening, sir.
you. Good.